Next, question 13. We are supposed to predict how the hardness and the conductivity of the C60 fullerene will compare with that of the diamond and the graphite. So we need to do a very quick recap of fullerene and diamond and graphite. So just give me a moment and I'll bring you back to the notes on that section. Okay, so if you are in your chemistry notes, there will be one section which is on diamond, graphite, and fullerene, which is this page here, page 50-51. Okay, let's do a very quick recap. So in a diamond structure, it's the hardest mineral that you can see. And why is it so hard? Because it's a giant covalent structure. So some of the key things that we are looking at will be the giant covalent structure. All right, and the giant structure. And what is joining all these carbon atoms together? This is actually very strong covalent bonds. And so we are seeing very strong covalent bonds here. And how about in terms of its electrical conductivity? So you see every carbon here is bonded to 4 other carbon atoms using all its valence electrons. Hence, the carbon will not have any other extra valence electrons that is not used and is a non-conductor of electricity. Okay, so if we take note, you may want to put it down as a non-conductor of electricity. And the main reason for this poor electrical conductor is because there are no delocalized electrons in the structure. And why are there no electrons, no delocalized electrons? As all the valence electrons are used in the bonding. Okay, so that's the first part on diamond. If you need to take down, then you will pause. Okay. Now, moving on, then we will look at graphite and fullerene. So graphite is a giant covalent structure again. So please take note, it's a giant structure again. And what's so special about this giant structure is that between these carbon atoms, we are seeing covalent bonds. So it's strong. Okay, the bonds are strong. However, between each layers of graphite, we are only seeing these dotted lines here are only very, very weak London dispersion force because carbon and carbon are non-polar. So the intermolecular forces will be weak London dispersion force. Hence, it's not very hard. It will be quite soft because, right, the layers are able to slip easily. So we look at this point here. Because of the London dispersion force, the layers are able to slip across each layer easily. Third, we are going to look at the electrical conductivity. So if you zoom into every graphite atom, you will see that this graphite atom is only forming 1, 2, 3 bonds. So the carbon only forms 3 bonds, but it has 4 valence electrons. So it's only using 3 out of its 4 valence electrons in the bonding. And so what happens to the last electron then? The last electron will be contributed into the delocalized system of electron cloud. So you put it in a delocalized system of electron cloud, which will be able to move across this giant plane. So these electrons will be able to move across this whole entire giant plane to conduct electrical energy. So graphite will therefore be an electrical conductor in the solid state in the parallel arrangement. Then we move on to fullerene. Fullerene is like the soccer ball. Remember, there is made up of hexagon and pentagon. So you can see the hexagon face, the pentagon faces. Okay? And it is not a giant. Okay, because it's only made up of 60 atoms. So therefore, it can't be a giant, 60 atoms, right? And this carbon, in this case, are or forming 3 bonds. So if you zoom into any carbon and you take a look carefully, you will find that it's forming this carbon is forming 1, 2, 3 bonds. And so we also have the same case whereby there is a delocalized electrons. However, there will be something different. So can you look at the bottom of the page? Okay, look at the bottom of the page. So you'll find that they are not giant molecules. They are simple molecules and they do not conduct electricity, even though there are delocalized electrons inside each ball. So if we call this fullerene a ball of fullerite C60, there's delocalized electron inside each C60 fullerene. But overall, it does not conduct electricity because it's a very small molecule of 60 atoms, 60, 60, 60, and 60. So can you imagine these are all the atoms? Okay, the electrons are inside the ball, but the electrons are not able to move across to the next one in order to facilitate the flow of charges. So in order for it to flow the charges across, then the electrons must be able to move across each C60. But the delocalized electrons are within each C60 and not able to move to the next and the next. And therefore, even though it has delocalized electrons, but you do not see that it is able to conduct electricity. Okay, and the next thing about C60 is that if we go back to this structure, yes, this is its picture of C60, and therefore between these balls of molecules, there are intermolecular forces. So all these are the intermolecular forces, and they are again very weak London dispersion force. Okay, because carbon atoms are non-polar. So the whole molecule is non-polar. So non-polar molecules will usually have only London dispersion force. So it's not strong, it's weak. And therefore, we don't expect C60 to be hard. It will also be soft because of the weak London dispersion force that is found between the molecules. All right, so after a quick revision of these 3 things in the question, let's go back to the assignment and look at the question one more time. So they say predict, explain the hardness, which we have already covered, conductivity compared to diamond and graphite. So you try to write it out in your own words, but we have already gone through all the points that's needed for this question.